Hello.
Oh my gosh. Hello?
Hello. I'm just going to wait a few more minutes. So how is the audio? Can you hear me?
It's much better.
Oh, good. I'm glad to hear. Great. Okay. Well, I think we'll go ahead and get started. Did anybody have any questions for me? Okay, can you guys see the PowerPoint? Okay, so we're going to take a look at the problems about surface area that we tried to look at yesterday. I'm going to assume you can see the PowerPoint unless you say otherwise. So we're going to take a look at problem number 12 to start with. And it wants to know which one of these three shapes has the largest surface area. A right circular cone with a diameter of base 1 and a height 1, or a right circular cylinder with a diameter of base 1 and a height 1, or a sphere that has a radius of 1. So first we're going to start with the cone. In order to find its surface area, we're going to need to figure out the slant height. And in order to find the slant height, we're going to think about a right triangle that goes right up and down through the middle of the cone and then out towards the side. So the slant height will be the hypotenuse of that right triangle. And we'll have one side of the triangle is 1/2 and the other side of the triangle is 1. So we'll do 1/2 squared plus 1 squared equals the slant height squared. And if you solve that, you should find that the slant height is the square root of 5/2. So then when we find the surface area of the cone, it's A, that's the area of the circle, that's the bottom, plus 1/2 times C times L, so 1/2 times the circumference times the slant height. And we get pi r squared plus 1/2 times 2 pi r times that slant height. R again is 1/2, so we have pi times 1/2 squared plus 1/2, and then we do 2 pi r, so we have 2 pi times 1/2 times L, which is the square root of 5/2. And so we get pi/4 plus the square root of 5/4 times pi, And that comes out to be about 0.809 times pi. Next, we're going to look at the cylinder. We're going to do 2 pi r squared. That's because we have the top and the bottom that are circles. They have an area of pi r squared. And then 2 pi r times the height. And that's the outside part of the cylinder. I like to think of that as the label off of like a soup can. It's going to unroll to make a cylinder, and one side, it's going to unroll to make a rectangle, and one side of the rectangle is 2 pi r, and the other side is the height. So then when we plug in r, which was 1/2, we get 2 pi times 1/2 squared, plus 2 pi times 1/2 times 1, and that will all come out to be 1.5 pi. Next, we're going to do the sphere. So the surface area of a sphere is S equals 4 pi r squared, and then we'll plug in 1 for r, so we have 4 pi times 1 unit squared, and that makes 4 pi square units. So it turns out that the sphere has the largest surface area. Next, we'll take a look at problem number 16. It says a new jumbo-sized cereal box is to be produced. Each dimension of the regular-sized box will be doubled. How will the amount of cardboard required to make the new box compared to the amount of cardboard required to make the old box? So we're going to suppose that the original box was X units by Y units by Z units. And then we're going to figure out the surface area. Okay, that'll tell us the amount of cardboard, assuming that there's no overlapping cardboard. And so we have 2 faces that have an area of X, Y, and 2 faces that have an area of X, Z, and then 2 faces that have an area of Y, Z. So we have these 3 different areas, and each one we multiply by 2 because there will be 2 faces that have that area. And that gives us our total surface area. Okay, so we know that the total surface area of the old box is 2xy plus 2xz plus 2yz. And now let's try to find the surface area of the bigger box. Since the old box was X units by Y units by Z units, and all dimensions get doubled, the new box will be 2X units by 2Y units by 2Z units. So we'll find the surface area, which will tell us the amount of cardboard, assuming we don't have any overlapping cardboard. And so we have 2 rectangular faces whose area is 2x times 2y, and that gives us 4xy. And then we have 2 faces whose area is 2x times 2z, that gives us 4xz. And then we have 2 faces whose area is 2y times 2z, and that gives us 4yz. We're going to multiply each of those amounts by 2 and add them up, and that gives us the new surface area. Okay, so notice that the 2 and the 4 for each one of these will make an 8. So we'll have 8xy plus 8xz plus 8yz. And then we could pull a 4 out in front. And so this gives us 4 times the surface area of the old box, because the amount in here is the surface area of the old box. Okay, so when we double each dimension, we end up quadrupling the surface area. The surface area got multiplied by 4. Okay, next we're going to take a look at problem number 20. It says, given a sphere with a diameter of 10, find the surface area of the smallest cylinder containing the sphere. So since the diameter is 10, that means that from one side here to the other side will be 10, And same thing from the top to the bottom. Since the diameter is 10, we know that the radius will be 5 units. And the height of the cylinder will be 10 units. We need to find the surface area of the cylinder. So I'm going to start with the top and the bottom. They're circles, and the area will be pi r squared. We know r is 5 units, so we end up with 25 pi square units for the top and then for the bottom as well. And then next, we want to find the area of the lateral face. So again, that's like the label from a soup can. And if we were to unroll that label, we would get a rectangle. One dimension of the rectangle is the circumference of the circle, which is 2 pi r. And then the other dimension is 10 units, the height of the cylinder. So we get 2 pi times 5 units times 10 units. That gives us 100 pi square units. To get the total surface area, we have 2 circles, and each circle had an area of 25 pi, so we get 2 times 25 pi square units, plus the rectangle, which was 100 pi, and that gives us 150 pi square units, or about 471.24 square units. Okay, next I want to think about why is the surface area of a cone equal to equal to A plus 1/2 CL. So I've got my cone here, and we have the circle on the bottom, which corresponds to this circle here in the net. So we have the circle on the bottom, which corresponds to the circle on the net. And then if we were to flatten out the top, we would get a partial circle. So let's assume that we're dealing with a cone that has a base radius of r, a height of h, and a slant height L. The net for the cone will have a circle, which is the base of the cone, and a part of the circle, which is the lateral face of the cone. And the radius for the complete circle is r, the radius of the base, while the radius of the partial circle is L, and that's the slant height. We can find the area of the base. It's just pi r squared. Next, we're going to find the area of the partial circle. So if we had the whole entire circle, we would do pi times L squared. We only have part of the circle, so we need to figure out what fraction of the circle we have and then multiply the pi L squared by that fraction. So imagine the big circle, if we had the complete circle, as a track. If you ran all the way around that, how far would you have run? You would have run the circumference of the circle. Okay, so it would be the circumference of the big circle, which is 2 pi L. Instead, you're going to run from right here at the bottom all the way around to right over here. We need to figure out how far that is. But think about if we folded this back up, it would fold up to make the cone. So the distance around the round part of the partial circle is going to be the same as the distance around the base of the cone. And the distance around the base of the cone is the circumference of the small circle, which we know is 2 pi r. So the fractional part of the large circle that you've run would be 2 pi r over 2 pi L. And the 2's will cancel and the pi's will cancel to reduce this fraction down to just r over L. That's the fractional part of the circle. So the area for the partial circle is pi divided by L times the area of the complete circle, pi L squared. And we have an L on the bottom that'll cancel with an L on the top to reduce it down to R times pi times L. And r times pi is half of the circumference, right? Because circumference is 2 pi r. So we have half of that. And so that gives us the total surface area. We have the area of the little circle, which was A, plus 1/2 CL. Did anybody have any questions so far? Okay. Well, then we're going to take a look now at section 11.1, which is all about probability. Oh, we do have a question. Oh, your sound keeps going in and out. Okay,
Yeah.
hold on. Yeah. Hang on just a second. Yeah, I need your help.
Let me know. So,
Okay, so I turned the thing on and I'm trying to connect. What do I do?
well, click the network, think about the world icon down there with nothing going
This
on.
thing?
Yeah. Was it not working before or something?
They said they were having trouble hearing.
Yeah.
Is that better?
Yeah, much better.
Oh, good. Okay. Thank you for letting me know. All right, so we'll keep going. Okay, so can you see the PowerPoint on probability?
Mm-hmm. Yeah.
Excellent. Okay, so we're going to talk about section 11.1, probability and simple experiments. And we're going to start with some definitions. An experiment in this section about probability is the act of making an observation or taking a measurement. And an outcome is one of the possible things that can occur as a result of the experiment. So if your experiment is flipping a coin, then the outcome, you could get heads or you could get tails. And the set of all possible outcomes is called the sample space. And an event is a subset of that sample space. So we're going to take a look at problem number 2. It says list the elements in the sample space for each of the following experiments. The first one is just a quarter is tossed. Okay, and we want to list the sample space, which is a set of all the possible outcomes. So the sample space is just heads or tails. That's what can happen. Next, a single die is rolled with faces labeled A, B, C, D, E, and F. And we want to find the sample space, the list of all the possible outcomes. So the sample space is A, B, C, D, E, F. Part C says a regular tetrahedron die. Okay, die is just the singular of dice. And so we just have one, and it has 4 faces that are labeled 1, 2, 3, 4, is rolled, and the number on the bottom face is recorded. So the possible outcomes are 1, 2, 3, and 4. It's just what can you get? 1, 2, 3, 4. And then part D, the following red, blue, yellow spinner is spun once. It says all sectors are equal in size and shape. And so the outcomes, you could either land on red or blue or yellow. And it doesn't matter what order you list those in. So if you wrote that the sample space was yellow, blue, red, that would be fine also. Next, we'll take a look at number 3. An experiment consists of tossing 4 coins. List each of the following. The sample space. So since we're tossing 4 coins, we want to see what do we get on the first coin, what do we get on the second coin, what do we get on the third coin, and what do we get on the fourth coin. So we could have heads on all 4, or heads on the first 3 and tails on the last one, or 3 heads and get a tail on the third, or 3 heads and a tail on the second, or 3 heads and a tail on the first. Okay, so I tried to keep these in order. So I did 4 heads, 3 heads, and then 2 heads, and then I did 3 tails, and then all 4 tails. And there were 16 total combinations. Part B was to list the event of having a head on the first coin. So I know the first coin will be heads, and I don't know what I get on the second or the third or the fourth. So I could have the first coin heads and all the rest of them tails, or the first is heads and then second is tails, third is tails, and the fourth is heads, and so on. So I have 3 tails, 2 tails, and then 1 tail, and then all of them being heads. So there were 8 of those altogether. Part C is the event of 3 heads. I don't know which ones have 3. So I could have the first 3 being heads and the last one being tails, or the tails could be on the third, or the tails could be on the second, or the tails could be on the first. And part D says the event of a head or a tail on the fourth coin. So I have no idea what happened on the first coin or the second coin or the third coin. All I know is that I either got a head or a tail on the fourth coin. So I actually don't know anything. Okay, and so I just have the same thing as the original sample space. I could have anything happening. Okay, part E is the event of a head on the second coin and a tail on the third coin. So I don't know what happened on the first coin. I got a head on the second, a tail on the third, and I don't know what happened on the fourth. So I could have a head on the first one and on the fourth one. I could have a head on the first one, but a tail on the fourth one, a head on the first, or a tail on the first one and a head on the fourth, or both the first and the fourth could be tails. Okay, so there were only 4 ways to fill that one in. Next, we're going to look at problem number 4. It says an experiment consists of tossing a regular dodecahedron die, which has 12 congruent faces numbered 1 through 12. List the following. The sample space. Okay, so the sample space is just all the possible outcomes. And so we could get a 1 or a 2 or a 3, etc., all the way to 12. Part B is the event of an even number. So this time we're just going to write down the even numbers. So I'm calling that event 1, which is I got a 2 or a 4 or a 6, an 8, a 10, or a 12. Event or part C, the event of a number less than 8. So I'm going to call that event 2. And if I get something less than 8, I must have gotten a 1, 2, 3, 4, 5, 6, or 7. Event D is getting a number that's divisible by 2 and by 3. So let's think, what could the number be if it's divisible by 2 and 3? It could either be a 6 or a 12. And part E is getting a number that's greater than 12. Well, since the numbers only went up to 12, there aren't any outcomes in this event. This event is the empty set. Problem number 5 says identify which of the following events are certain, possible, or impossible? Part A, you throw a 2 on a standard 6-sided die. That can happen. It's possible. Part B, a student in this class is less than 2 years old. That's not possible. That's impossible. And part C, next week has only 5 days. Well, a week has 7 days, so that's also impossible. Next, we have some more definitions. First, we're going to look at the probability of an event with equally likely outcomes. Suppose all the outcomes in the non-empty sample space are equally likely to occur. So we have some outcomes and they're all equally likely. And we're going to say E is some event. N of E is the number of outcomes in the event. And N of S is the number of outcomes in the sample space. Then the probability of an event, E, we're going to call that P of E, and it's just the number of elements in the event divided by the number of elements in the sample space. Okay, so if assuming the events are, or the outcomes are equally likely, we just find the probability of an event by counting up how many elements are in the event and dividing by how many elements are in the sample space. If the probability of an event is 0, then the event is impossible. If the probability of the event is 1, that means that it's certain. And remember, 1 is the same as 100%. Okay, we're going to be thinking about 2 different kinds of probability. The first one is called experimental probability. And here, we're going to think about having some data that's been collected, and the probability of an event is the number of times the event occurred divided by the total number of trials. So if you were thinking about rolling a die, if you actually rolled a die 100 times and you got a 2 10 times, then the probability of getting a 2 would be 10 out of 100. To find a theoretical probability, you don't collect data. Instead, the probability is simply the number of favorable outcomes divided by the number of possible outcomes, assuming that all the outcomes are equally likely. Okay, next we're going to take a look at number 7. It says a die is rolled 60 times with the following results recorded. So we can see that we rolled a 1 10 times, we rolled a 2 9 times, we rolled a 3 10 times, we rolled a 4 12 times, we rolled a 5 8 times, and we rolled a 6 11 times. And we want to find the experimental probability of the following events. Okay, and we're doing experimental because we're looking at having actually performed an experiment and recording some data. So the first thing we're going to look at is the probability of getting a 4. So the probability of getting a 4 is just the number of times that event occurred divided by the number of trials. And we rolled a 4 12 times, and there was a total of 60 trials, so the probability is 12/60ths, which reduces to 1/5, which is the same as 0.2 or 20%. Next, we want to find the probability of getting an odd number. Okay, it looks like we only have 10 more minutes left. So we'll see what we can do in 10 minutes. The probability of getting an odd number means we're going to get a 1 or a 3 or a 5. And we know we got a 1 10 times, a 3 10 times, and a 5 8 times. So the number of times we got a 1, 3, or 5 is 28 out of the 60 trials. So that reduces down to 7/15. Part C, the probability of getting a number greater than 3. Well, if it's greater than 3, that means it's 4 or 5 or 6. We got a 4 12 times, 5 8 times, and 6 11 times. And so that probability is 31 out of 60. Problem number 10 says 2 standard 6-sided dice are thrown. If each face is equally likely to turn up, find the following probabilities. And I grabbed this table right out of your textbook, and it just shows the different possibilities. So you could get a 1 both times, or a 1 the first time and a 2 the second time, etc. And the second part shows you what you get if you add the two numbers together. So part A is the probability of getting a 4 on the second die. So I'm going to be looking at this column right here. We're going to use the picture from page 493 in your book. There are 36 different combinations, 6 of which have a 4 on the second die. So the probability of getting a 4 on the second die is 6 out of 36, or 1/6. Part B, the probability of getting an even number on each die. So we could get a 2 and a 2, or a 2 and then a 4, a 2 and then a 6, a 4 and then a 2, a 4 and a 4, a 4 and then a 6, a 6 and then a 2, a 6 and then a 4, or a 6 and then a 6. So there's 9 different ways for it to happen out of the 36 different possible outcomes, and that reduces down to 1 out of 4. Part C is getting a total greater than 1. So here they're talking about adding the two numbers. And notice, no matter what you roll, when you add them up, you get something bigger than 1. So all 36 combinations have a total greater than 1. So the probability that the total is greater than 1 is 36 out of 36, which is 1, or 100%. Problem 11 says a card is drawn from a deck of 52 playing cards. What is the probability of drawing each of the following? And so I grabbed the picture out of your book that shows the possible cards in the deck of 52 cards. Part A says a black or a face card. So there are 2 black suits, and there's 13 cards in each suit. So I know there's 26 black cards. The face cards are the jacks, the queens, and the kings. So there's 3 face cards in each suit, the jack, the queen, and the king. And there's 4 suits, the diamonds, the hearts, the spades, and the clubs. So there's 12 face cards altogether. And the probability of getting a black or a face card is just the number of black or face cards divided by the total number of cards. And so we have 13 plus 13 gives me 26, 27, 28, 29, 30, 31, 32. There are 32 cards out of 52, and that reduces down to 8 out of 13. Part B is getting an ace or a face card. So there's 4 aces plus the 12 face cards. So this probability is going to be 16 out of 52, which reduces down to 4 out of 13. Part C is the probability that we get neither an ace nor a face card. So this is going to be the number of cards that are neither ace nor face cards out of the total. And this will be 36 out of 52, which reduces down to 9 out of 13. Part D, the probability of getting a card that's not an ace. Remember, there's 4 aces and there's 52 cards altogether. So the number of cards that aren't aces would be 48 out of 52. And that reduces down to 12 out of 13. Okay, we'll take a look at number 12 real quick here. It says a dropped thumbtack will land point up or point down. Do you think one outcome will happen more often than the other, and which one? And honestly, I didn't really have any idea, so I just guessed maybe it'll land point down more often. Part B, the results for tossing a thumbtack 60 times are as follows. So somebody collected some data, and it landed point up 42 times and point down 18 times. It says, what's the experimental probability that it lands point up? Well, 42 out of 60 times it landed point up. That reduces down to 7 out of 10, or 0.7. Point down, it landed point down 18 out of 60 times, which is 3 out of 10, or 0.3. Part C says, if the thumbtack was tossed 100 times, about how many times would you expect it to land point up? So we know that it lands point up 70% of the time. So we would expect 70 out of 100 times that it would land point up. How many times would we expect it to land point down? Well, it lands point down 30% of the time. So I'm going to expect 30 out of the 100 times it lands point down. Number 13 says we have a key ring with 5 keys on it. One of the keys is a car key. What is the probability of picking that key? Well, it's just the number of car keys out of the total number, which is 1 out of 5. 2 of the keys are for your apartment. What's the probability of selecting an apartment key? That's going to be the number of apartment keys out of the total number, which is 2 out of 5. Part C, what's the probability of selecting either the car key or an apartment key? That's the number of keys that are either for the car or the apartment out of the total. So that's 3 out of 5. Part D, what is the probability of selecting neither the car key nor the apartment key? And that's going to be the number of keys that are neither for the car nor the apartment. And that would be 2 out of the 5 keys. Okay, so I think we're going to call it quits for today. Did anybody have any questions about anything? Okay, well, I appreciate everybody coming. I hope you're all doing well. You do have some problems on my lab to work on. I will certainly try to put this video up. I haven't had very much luck with doing videos in Zoom so far, but I've got my fingers crossed that I will be able to put it up. If for some reason I don't manage to put up the video, would you like the PowerPoint? Okay, so if I can't put the video up, I will put up the PowerPoint. Anything else I can do for anybody?
Oxygen level is? Yeah, pulse oximeter.
Okay, well, I hope you're not getting too bored at home. I appreciate you coming and looking at some probability and some surface area problems with me. All right, so I'll probably see you again tomorrow. Did you like this better than what we did yesterday? Did it work better for the most part?
Yeah, it worked really well.
Oh, good. I'm